So three-dimensional space, lines, right? We got to talk about lines. Think back to, say, when you were studying the XY plane, right? What's the first thing? One of the first things you learned in two-dimensional space, right, in R2 is that, you start with how to think about lines, right? You do y equals mx plus b, and, there's also the point slope form, right? You do y minus y1 equals mx minus x1, right? So the lines, they're one of the easiest shapes to understand. They're one of the most important shapes. So just like you start off with lines in R2, we want to also start off with lines in R3. How can they be represented in R3? So there's one nice way, really nice way to represent lines that corresponds to mx plus b, and there's one really nice way to represent lines that corresponds to point slope form, right? So we're going to have kind of a three-dimensional parallel of each of these, right? So I'm going to call this first. I'm going to call this the mx plus b version, right, of a line in 3D. But we're going to do it using vectors, right? So this is going to be just kind of a vector form of a line, right? And it's sometimes you could call it vector form. mx plus b form. Nobody actually says that except me or someone else who's making that same analogy. But sometimes it's called the vector form of a line. Sometimes it's called the parametric form of a line. Same. These are both perfectly good ways to call it. The way that you specify a line with this is you say, okay, I have, I'm going to generate my line by telling you where to start. So we give some initial point, just like B, the y-intercept is some initial point, right? So we're going to specify some initial point, and that initial point we're going to specify with a vector. So imagine the tip of that vector, right? That's going to be our initial point. So I'm going to call that initial point B, just because it reminds me of the y equals mx plus b form, right? You don't have to call it B, but let's call it B. So let's call this some initial, right? Some initial starting point for your line. And then you pick some direction, right? How are we going to specify the slope? So you can think of this as M. You could write it as vector M, but it's very non-standard to do so. Usually people use D, lowercase d, for direction, right? It's a direction vector of a line, but it's basically playing the role of M, right? So you can say that this is a direction vector. And so then what you do to get all the points on your line, right? So we're going to build this line, which we'll call L. So we'll say L of t, right? This is the parameter. This is why it could be called a parametric form. What you do is you take your starting point, B, and then you add to it every possible scalar multiple of the direction vector D, right? So what we're doing there is we're saying B gets us to our starting point. So this black vector is the vector B. And then let's say our direction vector will represent in orange. So you can do, this point would be B plus 0 times the direction vector, right? And then say this point here could be B, so this would be L1 would be B plus 1 times the direction vector. And then, you could go out here to L2, L of 2, right, would be B times 2 plus 2 times the direction vector, and so on, right? And then you can go the other way too, right? You could go L of -1, right, would be B minus the direction vector, -1 times the direction vector, and so on, right? So you're taking from that starting point B, you're traveling by every scalar multiple. You're adding every possible scalar multiple of the direction vector to that point B, and that gets you all the points up and down the line, right? So it's going to generate all of these locations, right? And you get an infinite line going nice and straight in both directions forever, right? So that's the essentially mx plus b form of a line, right? If you rewrite it just slightly, rearrange it to look like this, right? See, now it looks just like mx plus b, right? This tells you where to start. This tells you what the direction is, right? It's typically with vector notation, you don't write vector d times the scalar t. You can, and everybody would know what you're talking about. It's fine. But typically you put the scalar in front. So that's why it's t times d instead of d times t, but it means the same thing. So there we go. So that's vector form or parametric form of a line. One thing that's nice is, you can keep this all packaged up like that, or you can give it coordinates, right? So if you say b, if you have some initial x naught, y naught, z naught, some initial points, initial coordinates that define b, and then vector d maybe is defined by some scalars ABC, right? Then what's nice is um, you can expand this, right? You can expand this to get L of t equal to what? So this is our vector B is x naught, y naught, z naught, right? Plus t times d is ABC. And then you can add these together, x naught plus AT, y naught plus BT, z naught plus CT, right? So this is how I have it written up here. This is all sort of, um, compressed into a really tidy vector form, right? This down here it's really the same formula, right? But this is sort of a parametric form, right? It's two sides of the same coin. It's just whether you're keeping it written using vector notation or whether you're expanding out those vectors into their components. But either way, you're doing the same thing. So that's vector form or parametric form of a line. Right? It's a very nice way to represent a line using our vector geometry, where you're basically just doing mx plus b, but with vectors. Oh, okay. Now, here is another form you can get to from here. So take this parameterization. So now for our next adventure, right, eliminate t from the parameterization, right? Start with how can you start with a parametric curve and get a Cartesian equation for it, or several Cartesian equations for it? What you try to do is use some algebra or some identity to eliminate t, right? In this case, probably the easiest way to do it is just to say, what do I have here? I have that the x, y, and z coordinates are specified by these linear formulas, right? X naught plus AT, Y naught plus BT, and Z naught plus CT, right? So take each of these equations from our parameterization and solve them for t. So here, if I just do the regular algebraic thing and solve this for t, I get x minus x naught divided by a. That would be t, right? And then in the second one, I'd have y minus y naught divided by b. In this third one, I'd have z minus z naught divided by c, right? Okay, well, if all three of those quantities are equal to t, then they're all equal to each other, right? So here, those are all equal to each other. This brings us to what's called symmetric form of a line. So symmetric form is you just say those three quantities must all be equal to each other since they're all equal to t, right? So you just say the line, and what line is it? It's the line passing through the point, right? If you have this point x naught, y naught, z naught, because that was b, that was our initial point on our line, right? Vector b, right? So this is passing through this point, right, with direction vector ABC, right, is given by what Cartesian equations? Like we said, just equate these three quantities, right, is given by x over x naught equals a. What? X minus x naught over a equals, there we go. That's a synchronizing error between the pen and the mouth there. There we go. So there we have our equations, right? X minus x naught over a equals y minus y naught over b equals z minus c naught over c. Those three quantities must be equal. Right? So there we have what's called symmetric form of the line, right? This equation, right? Now, my claim is that the first form was really just y equals mx plus b in 3D, right? My claim is that this one is point slope form, right? Why is this point slope form? So here's how to see that this is point slope form. Not exactly point slope form, but the analogy of point slope form. If you look at this, right, ignore the z coordinate for a second. Not forever. We need it for our 3D. But for sake of our analogy, ignore that z coordinate for a second. Look at this equation and just multiply both sides by b, right? If you multiply by b, what happens? You get y minus y naught equals b over a x minus x naught. There you go. There's point slope form, right? So the first two pieces of symmetric form is literally point slope form. And now you just have one more condition to make sure that the z also has a linear relationship to x and y, right? So that's our point slope form there. Just right, it's just the 3D version of that. Now, one little warning here. Obviously, symmetric form requires that A, B, and C are non-zero, right? That's where the vector form, parametric form, this version is maybe a little better. Because up here, you could have A, B, or C be zero, and nothing bad happens. It doesn't break anything in this formula, right? This green or blue way of writing a line. You could do that and have zeros wherever you like. But down here, right, if you have A, B, or C is zero, it doesn't work, right? So that's one thing to think about. In a case where you do have A, B, or C equals zero, you can still write it using Cartesian equations. It's just that you need an equation where you have typically like x or y or z is some constant, right? The line just isn't varying with respect to one variable. So you'd have you'd still have two equalities, but just one of them is setting it to a constant. So, which you can actually see up here, right? If you set, like, say A was zero, then that first equation would tell you that x of t always equals x naught, right? So that's how that fits into the picture. Okay, let's look at a little example here. So, for example, let's do some line representation. Let's find representations in both parametric and in symmetric form of the line passing through the points, let's say 0, 1, 1, and -1, 3, 2. Right. So we specify 2 points in 3 dimensions, and we want to find the line containing them, right? Because 2 points, 2 distinct points determine a unique line. That's true in 2 dimensions. It's still true in 3 dimensions, right? So let's see if we can find this line. So how would I do this? Well, I would have here, I'd have x, y, and z, right? Right, so I have 0, 0, 1, 1. So 0 in the x, and then I have 1 and 1 on the y and z axes, right? And then I have this point -1. Oops, that's not what I did. There we go. 0 on the x, 1 and 1 on the y and z. There we go. There we go. Now the picture matches. Then we had minus 1, 3, 2. So I go minus 1 on the x. We do 3 on the y and 2 on the z, right? So I have this point kind of right up here. You can imagine that little box. There's a point up there, right? So I have, say we call this point A and point B, right? There's A, there's B, right? And so now what I can do is I can pick, I'm going to start with the vector parametric form. That one's a little easier to start with because I can pick either point to be vector little b. So I'll choose A, right? The initial point to solve this problem, right? I'll start with this initial point B, will be x naught, y naught, z naught is going to be 0, 1, 1, right? So that gets me to the point A. And now what do I need? I need to pick the direction vector from there, right? So what I represented in orange in the general case. So what is vector D going to be? So vector D is just going to be the point B minus the point A, right? It's going to be the difference in those coordinates, right? If we subtract the coordinates there, we're going to get the vector that brings us from the one to the other, right? So minus 1, 2, 1, that'll be the direction vector for this line because it's the vector that you would add to A to get to B, right? Better known as B minus A. Right? So that's our direction vector, right? So now what do I want to do to get the line that goes through them? I just want to add to location A, to point A, right, which I'm calling vector little b. I want to add 1 copy of D, 2 copies of D, 3 copies of D, half a copy of D, a tenth of a copy of D, negative 1 copies of D, negative 2 copies of D, negative 3 copies of D, and so on, right? So what is that to build that line? To build that line, which this is line, right, line AB is what is, which, in the other notation, in our vector notation, if we call it, if this is line L of t that we drew here, right, what would that be? It would be our starting point, little b, right, plus t times d, right, our direction vector. So in this case, what do we have? I have 0, 1, 1 plus t times d minus 1, 2, 1, right? And this, so you could leave it there, or you can combine it and say, okay, this is negative t, 1 plus 2t, 1 plus t, right? And you could combine it into just a single parametric form. Either one's fine. So this is a perfectly good answer. This is a perfectly good answer. Now you might, one thing to note, one question you might have, this right here, this was a little bit arbitrary. I picked point A as our starting point. If you wanted to pick B as your starting point, minus 1, 3, 2, you can. Totally valid, right? It doesn't matter whether you pick point A or point B. You just need some point on the line to start with. It's really not important which one you start with, right? You'll get the same line either way. You'll get a different parameterization of it, but it's the same line, right? There's not a unique way to parameterize a curve. So these are both perfectly good ways to go. Then we have our other form, right? Our symmetric form. What is the case in our symmetric form? How do we get to symmetric form? The way we get to symmetric form, remember, is we solve for t, right? So I have x of t is negative t, y of t is 1 plus 2t, and z of t is 1 plus t, right? Solve each of those for t to eliminate t. So I say t is negative x in the first equation, right? T is y minus 1 over 2 in the second equation, and t is z minus 1 in the third equation. And now equate those all to each other to get the symmetric form. So negative x equals y minus 1 over 2 equals z minus 1. right? That's our symmetric form, right? So that's our answer in symmetric form for this line. And notice this looks like how you'd want it to look, right? If you want to be a little more specific about it, right, you could say this is, and put all the like placeholders in. You could say this is x minus 0 over negative 1, right? Y minus 1 over 2, and z minus 1 over 1. That's what I mean by placeholders. Any place where you're dividing by 1 or adding or subtracting 0, put the 1 or put the 0 there. If you want to be a little more explicit, it just helps you see that you got it correct. It's not necessary, but it's kind of nice to see it that way. Because what do I have here? I have 0, 1, 1, right? That's my initial point, is 0, 1, 1, right? 0, 1, 1 is point A, right? Then you have what in the bottom? That's our orange, right? That's our direction vector, minus 1, 2, 1. That was our D, right? So that's the direction vector D, right? Minus 1, 2, 1 is our direction vector D. So the denominators in symmetric form, they always give you the direction vector. And honestly, if you didn't want to like do this algebra here, and you wanted to just skip right to here by saying, hey, it's the line that starts at this point, number, 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 and then has this direction, number, 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 you could totally do that, right? I'm sort of just showing the algebra that connects those two forms, right? But you could also skip directly to the symmetric form if you wanted, for just given the information. We could have done symmetric form first, right? By just saying, here's where I want to start, and put those numbers in the x minus, y minus, z minus, right? Put those numbers up top, and then say, oh, here's the direction vector, and put those numbers in the denominator. I could have started with symmetric form, right? But I just wanted to kind of connect the two. So, all right, there we go. So there's an example of, these are the two main ways that we represent lines. And then here's an example of finding one, right? We're given 2 points. We want the line through that point, and we represent it 2 different ways. Great, thanks. On to planes, the next mission after lines. Standard next mission in 3D. Lines, then planes.